All right, so we've talked about parent functions now, and we know what the characteristics are. The characteristics of the parents generally are the characteristics of any other function in that family. So the wording I always find kind of interesting when we talk about functions and this idea of parent functions and families of functions, because I don't think it's a mistake. I think whoever came up with this idea of using this kind of terminology was very deliberate about it. Because when you talk about families of functions, they are generally functions that somehow came from the parent in the first place. They were somehow created by using the parent to get another function of the same type. So having some sort of absolute value function came from the absolute value of x somehow. Having some sort of quadratic function usually came from some transformation that was done on x squared. Okay? And so what we're going to spend a little bit of time on now for the next few lessons is the idea of what happens when you take a mommy function and a daddy function and make little baby functions. Okay? The idea is, how do we create new functions knowing these parent functions now? Knowing that these are sort of the basic building blocks, what are some different ways that we can create new functions? Well, one of them is with this idea of transformations. We talked about this quite a bit last year. So I'm hoping that these couple of examples that we can go through fairly quickly, and that you kind of remember what the transformations are. But this is an important topic to make sure we really do remember, because the transformations work with any function. Okay? Regardless of whether we're talking cubics or square roots or greatest integer function, that bizarre stair-step thing. Transformations work with all of them, and they work the same way with all of them. Okay? So, when we talk about transformations, we oftentimes see this general statement as a way of showing that the transformations can work for any function. So we're saying if I want to get some new function g of x, then I take whatever the parent f of x function was, and then I can insert numbers in 3 different places. I can multiply by some a value out in front of the whole function. I can subtract some h value inside of the function, or I can add some k value to the outside of the function. Now, when we talk about inside the function, what that means is, if, for example, I'm talking about a quadratic parent, the h value would be something that's with x in the parentheses before it actually gets squared. So it's inside the squaring function. Or if we're talking about the square root function, the h would be something that is inside the radical sign with the x. So when I use that terminology of being inside the function, it's like saying if you had to follow order of operations, you'd be subtracting h before you did whatever the function was doing. Squaring, cubing, absolute value, whatever. Okay? But then k is something that happens outside. So after you would do the squaring or the cubing or the absolute value, then you would add k, if you were following order of operations. There is also a b that gets multiplied on the inside, but in most cases, you can actually transform that into an a and then just deal with the a value, so we're not going to deal with b's. They're confusing. They confuse me. I've been doing this forever. So we're just going to stick with A, H, and K's. That's what we're going to be concerned about. So, A, H, and K. Let's do a quick review here. What effect can an A value have on a parent function graph to get a new G function graph?
Either, what's the word again? Stretch it or the other.
The other word actually kind of depends on the book you use. Some books use shrink, and some books use compress. I don't care which one you use as long as you use it correctly. I tend to go with shrink just because that's what I was taught, that you have stretch and shrink. And I have my little gremlin here. So if you kind of imagine that my little monster ball here, ooh, it's really sticky right there, yeah, is some function, right? Vertically means if I hang on to it at the top and the bottom and I stretch it, what happens to the appearance of my function? So that was the original, right? We're calling that the parent function. Vertically stretching it means up and down, so I gotta grab the top and the bottom. And if I start stretching it, what's gonna happen to the appearance? It gets narrower, right? This kind of starts to squeeze in. So when we're looking at graphs, if the graph looks narrower than what the original parent did, then we must have done a vertical stretch. Whereas if I start with that same parent and I do a shrink or a compression, then what happens to my graph? It's getting wider. Okay? So you're using your parent function as the comparison. And if the graph you're talking about looks skinnier, looks narrower, then we must be doing the vertical stretch. If it looks like it's wider than what the original parent was, then we must be doing a vertical shrink. Okay? So, let's be more specific here for just a second. What does the A value have to be to cause a vertical stretch?
Higher than 1.
Higher than 1? So what if my A value is a -3?
Oh.
Will that cause a vertical stretch?
Yeah.
Yes. But was it bigger than 1? What do you think, Peyton?
Well, if it's a fraction.
No, not quite. Because why?
If it's a fractional.
As in any integer.
Oh,
Integer,
Yes, but they don't have to be integers. Like if I said, what if A is 2.5? Is it an integer? No. Will it cause a vertical stretch? Yes. So yes, it's true, any integer will cause a vertical stretch, but that doesn't cover everything that will cause a vertical stretch. Does that make sense?
Anything in between.
So how can we deal with the fact, because Anthony's on the right track. If I have numbers bigger than 1, I'm going to have a vertical stretch. But if that's all I say, is A is bigger than 1, then that doesn't count for things like -3. So what's the simple little fix I can do to the A is greater than 1 that will account for -3 and -10 and -2.5?
Absolute value.
Bingo. if I say the absolute value of A has to be bigger than 1, then when I put the -3 in here and take absolute value of it, I'll be bigger than 1, and I can say that I'm doing a vertical stretch. Okay? All right, so what about then for vertical shrink? We talked about fractions. Any fraction, like 5/2 is a vertical shrink? No, that's a stretch because it's like 2.5. So what kind of fractions cause vertical shrink? That's not all fractions, then what fractions do? Fractions less than 1. So a -5/2 would be okay. Between 0 and 1.
Well, then
Okay, so what about -1/2? What does that do?
same thing, absolute value.
Yes. So we have to do the same thing. We have to say absolute value and then make it between 0 and 1. Okay, so if the absolute value of A is bigger than 1, we're going to have a vertical stretch. If the absolute value of A is between 0 and 1, then we're going to have a vertical shrink. Okay, and then we usually say by a factor of whatever the A value was. There we go. Okay, and that's for both of these, stretch or shrink. We say it's by a factor of that A value. So I can have a vertical stretch by a factor of 2. I can have a vertical shrink by a factor of 1/4. Okay? All right, does A affect our graph in any other way?
You can
Reflect it. So what does the A value have to be in order to reflect it? Say again? A negative number. So if A is negative, if it's less than 0, then we get a reflection through what? Not quite. The x-axis. So it's flipping from up to down, and that's a reflection through the x-axis because we're going from here to here. We do want to be specific about this whenever we have to describe transformations. We want to make sure we're saying it's a reflection through the x-axis. Because there are reflections through the y-axis, and that's what B does. So that B value that sometimes gets used, it has the effect of having a horizontal stretch or shrink, and it can reflect things across the y-axis. Okay, so even though we're not using B, we do have to be specific about A being a reflection through the x-axis because there are cases where reflections through the y-axis can happen. So we need to be specific about what we're talking about. Okay, anything else A can affect? That pretty much does it for A. But it's unique in that it does have this double possibility of what can change. Whereas with H and K, it's pretty much, it's this and it's this. That's it. But A's like, well, we can be doing this and we can be doing this. Okay? So H has what effect? Moves the graph left and right. It's our horizontal shift. Remember, H horizontal. So if h is positive, which way do we go? To the right. And if h is negative, then we'll be moving to the left. Okay, and then what about k? What effect does that k value have? Up and down. So it has a vertical shift. Oops. A little extra in there. All right, so if k is positive, which way are we moving? Up. And if k is negative, which way are we moving? Down. All right, does that all look familiar? Kind of remembering that from last year? All right, so let's actually try to put it in practice. So I want you to try this first. Okay? When we graph g of x, I would recommend that you kind of think of it as a three-step process. Okay? And not necessarily writing down every step of this, but think through it this way. First step, what parent function is this related to? Okay, sometimes it'll ask you, sometimes it won't, but whether it asks you to identify it or not, you should still be thinking it. Because you want to think, what does the parent of this thing look like? And I would even say, if you want, go ahead and make a quick sketch of that on your graph. Like, here's what the parent looks like. Okay? Second step is to then identify your A, H, and K. And usually I just write off to the side here, A equals, H equals, K equals. And just identify this value, this value, this value. So that then, once you know what those values are, once you go to do the graphing, you know what transformations you should be making. You know what the parent looks like, and now you know what these values are, so you know these are the kinds of changes I need to make in order to get the actual graph of G. And I recommend that you do them in this order. Do them alphabetically. So if you have something that's going to reflect and it's going to move up and down, do the reflection first, then move it up or down. Because you can get something very different if you do the move first and then reflect. Okay? So always carry it out in this order, A, H, K. Okay? Go ahead and try this first one. We want g of x to be x minus 3 cubed plus 2. You've got the whiteboards there in your baskets, and there are graphs on the back of the whiteboard, so do it on the whiteboard so we can see what you come up with. If any of you come across markers that don't work anymore, let me know and I'll replace them because I have a bunch of them, but I wasn't sure what were good and what wasn't good, and so I just threw a bunch in there and replaced them. You know you have graph on the other side of that, you can just use it's a little easier. And again, as I was moving things around, I found a bunch of markers. So, like, if I hand you 3 of them in a row that don't work, just hand them back to me. I'll find you another one because I just kind of went, oh, well, I got markers. I'll just put them in the pile and try them. Yeah, I got graph on the backside. That's a little easier. 30 more seconds. Finish them up. All right, let's see what you got. Hold them up.
It is.
I can't see it. All right, Rebecca, Mackenzie. Okay, Rebecca. Okay. All right, so we already identified the parent. The parent was what? Cubic. With each of your parents, because you're going to be doing a lot of these kinds of problems in this lesson and throughout this first chapter, and even beyond this chapter, a lot of times problems will come back to like, what's the parent, what's the transformation? And so if you can come up with a few key points for each of your functions, it makes the graphing quicker. Now, we know that every parent function kind of has that one key point, that one anchor point. But if you can come up with a few other points that are easy key points to come up with every time, then it just makes things faster. So when you're dealing with cube, what's the anchor point for the parent? Just the parent. What's that one point that's sort of the anchor of the whole thing? Origin, 0, 0. Okay? So if I just graph my parent in black here for a second, so I have an idea of what I'm working with, then what are a couple of other points that are pretty easy, obvious ones to graph on most of our grids? 1, 1, and -1, -1. So that's easy enough. 2, 8, so 1, 2, 3, 4, 5, 6, 7, 8. And then -2, 8. 1, 2, 3, 4, 5, 6, 7, 8. I think I counted that off, right? Okay. We don't need to be exact about our graphs, but we should be fairly accurate. Okay? So this gives us not only placement, but it also gives us a really good idea of what that width is. So if we have to do something with vertical stretching or shrinking, we have something fairly accurate to compare to. Okay? So this is what the parent cubic kind of looks like. Okay? Now, what's the A value that I have here? 1. Because there's nothing out here in front, so we assume we must have been multiplying by 1. What is the H?
3.
What is the K? Okay? So, we don't have to do any stretching, shrinking, or reflecting if A is just 1. Right? All of that happens if it's not A equal to 1. So what do we have to do? H being equal to 3 means we have to do what? Which way?
Right.
Right 3. And K being equal to 2 means we go up 2. Now, we usually do that with that key point, that anchor point, because it's easy. We know that normally cubic goes through 0, 0, and so now I'm going to take that 0, 0 point and I'm going to move it 3 to the right and 2 up. But technically what we're doing is we're moving every point on that graph 3 to the right and 2 up. It's not just the anchor point, it's every single point on that graph that's going to get that transformation. So, because I already have some other points here, it should be fairly easy to take each of those points and say, okay, so 3 to the right and 2 up. It goes right there. And this one, 3 to the right and 2 up. It's going to go right there. And this one, 3 to the right and 2 up. It's going to go right there. And 3 to the right and 2 up. It's going to go right there. Okay? So if we do the transformation with those key points as well, then we should get a really accurate looking g of x graph based on our a, h, and k values. Okay, so that's kind of the process. Now, whether you actually draw the parent or just think about it, it's up to you. Some of you are good at seeing that stuff in your head. Others of you actually need to see it on your paper. What I would ask is that if you're going to do both, then label. So when I go to graph, I know that you know this was just the regular parent, and this one is what I'm now saying g of x should be. If you're only going to do the g of x and not graph your parent, then obviously what you draw is what I'll grade. But if you do both of them, then just label them for me so I know which one you think is your actual final answer. Okay? Questions on this one? Okay, let's try another one. That one. Mm-hmm. Yep. Just a second. More seconds. All right, let's see what you got. Got a little variety. All right, so what do we want to do first? Even before that,
Identify the parent.
the parent, okay? Just so we know what we're dealing with. So what's our parent? Absolute value of x, right? Who thinks they can come draw it? Absolute value of x. Parent function. What's it going to look like?
Yeah. Okay, go.
Okay?
Oh, that one goes up more than the other.
That's okay. What do you think? Do you agree with that? Is that what the parent looks like? So again, she shows a couple of points here that she knew would be on it. 2, 2, negative 2, 2. The other thing that's easy about like absolute value and identity, the straight lined ones, is that they go corner to corner, right? They have a slope of 1, at least on this side for absolute value. So if you just kind of go corner to corner to corner to corner, you're going to get what you need. And then for absolute value, just remember the flip side is a reflection or negative 1. Okay, so that's what our parent is going to look like. Now for A, H, and K. What is my A value? Negative 2. What is my H value? Negative 1. Good. Remember, don't let that trick you into thinking positive 1. Because the original form is minus H. So the only way I get x plus 1 is if it's a negative 1 for H. All right, and for K? 4. Okay, so what effect is that negative 2 going to have on my graph? It's going to flip it, which we would say reflects. Okay? And there's going to be a vertical stretch. By what factor? 2. So I probably should go back for a second. Where I said that we say it's by a factor of A, we should probably say it's by a factor of absolute value of A. Because we don't usually include the negative when we talk about the factor of the stretch or the shrink. So if you go back to that part in your notes, make it factor of absolute value of A. Okay? What effect is my negative 1 going to have? 1 to the left. And what effect is my 4 going to have? 4 up. Okay? So if I go through these in order, the first thing I need to realize, whoa, hello. Not sure what I did there, but okay. First thing you need to realize is that we're going to have to reflect this. So this now becomes, whoa, that was interesting. Now I'm doing what you guys were doing the other day. Too fast. So we know we're now dealing with a V that's going to have to go upside down. Okay, now I'm not drawing it yet because that's just the first step, but it's just giving me an idea visually, like, here's what has to happen first. I'm going to turn it upside down, and then I'm going to stretch it by a factor of 2. So what that means is, when Taylor put in 2 for x and got 2 for y, if I'm going to stretch by a factor of 2, then putting in 2 for x should now give me what for y? 4. A 4. So it's saying every y value that I originally got for x is now going to get multiplied by whatever this factor is. So if originally going over 2 meant going up down 2, now going over 2 means going up down 4. Okay, if it was a factor of 3, then going over 2 would now mean going up down 6. Right? So whatever the original y value was of how far you went up or down for that particular x is now getting multiplied by this factor. So instead of just the 2, 2, I'm now talking about 2 and moving 4. So I have a point more like that. 2 and going 4. Okay, so we can see how it's going to get skinnier than what I had originally. But then I have to take all of those points and I have to move 1 left and 4 up. So I take 0, 0, and I go 1 left, 4 up. There's my new vertex. Okay, right about there. And then I can take these points. And I can go 1 left, 4 up. Nope, that wasn't right.
The origin's 2.
1. Say again?
The origin is supposed to be 2 spaces left.
Oh, I see. I got that in the wrong place. Okay, thank you. Fix that. Okay. 1 left, 4 up. Right there. There we go. So that looks better now. And then this one, 1 left, 4 up, puts me there. So now I can draw a fairly decent V. Get out of the shadow here. Which is upside down because I had a negative A. It's narrower than what I started with because I had that absolute value of A that's bigger than 1. And it's moved 1 left and 4 up. So the green graph is what I want to finally end up with as my g of x graph, as compared to this one, which was just the f of x, the parent. Okay, make sense? All right, so here's what I want you to do, and I don't know how far you're going to get, but for the next 20 minutes, we're going to do a scavenger hunt. Now, some of you, if you've been in my class before, may remember scavenger hunts. How's it not going down? There we go. Okay, and others of you may not be that familiar with it. So here's how a scavenger hunt works. You can see around the around the room, didn't quite get out to the world, just around the room, there are all of these papers up that have letters up in the upper left-hand corner. There's a graph in the top half, and there's a find the graph for some function on the bottom half. You are going to get recording worksheets that look like this. Okay? You can start at any one of these in the room. There are 20 of them. So you may not get through all 20, but we'll go as far as we can. Okay? So you can start at any one of them. It does not matter which one you start at. And wherever you start, that letter that's in the upper left-hand corner, you're going to write in that first column. So you know which paper you're starting with. Okay? And then what I want you to do is you actually start with what's written on the bottom half. So the function that's given to you on the bottom half, I want you to identify what the parent function of that would be. Okay? Then identify your A, H, and K values. And then just write really quick, so what would be the transformations of the parent? Would you be reflecting? Would you be doing a vertical shrink? Would you be moving left or right? Would you be moving up or down? Okay, that's what I want you to write over here. And then once you have that figured out, you then need to go find the graph that does that. So for example, if I start back here at D, and I realize that that function has a parent function of a quadratic, and I identify what my A, H, and K are, so I know what my transformations are, then I'm going to walk around the room and I'm going to find a parabola that matches those transformations. Make sense? And when I get to that sheet, whatever letter is in the upper left-hand corner of that sheet is what I put on the next line. And then I work that problem out. Ideally, it would be great if we could get through all 20, and you will know if you've done it correctly if you do the last problem here, and the graph that it takes you to is the first one you started with here. But as I said, in the 15 minutes that we've got here now, we may not get through all of them. Okay, so get as many done as you can in the 15 to 20 minutes. I want to come back really quick before we end the class because there's one more type of problem I want to show you really quick, but I want to go through this activity and get you up and moving a little bit first. Make sense? Okay, so you start with the bottom half. Well, you start by making sure you record what letter you're in that you start with. Then look at the bottom half to see what the function is. Fill out the paper based on that. Go find the matching graph somewhere in the room that's on the top half of the paper, and then repeat the process. So now that I'm over here at this graph, then I go to this function, work out the next line, and go find where that graph would be. And so on and so on and so on. Make sure that you do these and record these on your paper in the correct order, because that's how you'll check with me. If you actually do get all of them done, you'll come to me and say, okay, here's my order. A, C, F, R, K, whatever, and I'll just follow along with you and tell you, yep, that's the right order, or nope, you got a mistake right here. Okay? Any questions? All right, as soon as you get a paper, put your name at the top of it, and then go ahead and find a paper to start at. See how many you can get through. Okay, we're going to do this for about 18 minutes. Oh, there's one back here. I forgot. There you go. There's one. I'm going to read through the letters in the order they should be. I'm going to start with O, which may not have been where you started, but if you find where your O is, and then go through, and when you get to the bottom of the first page, one page, go to the next page, it should still work out. If you didn't get to all of them, then just kind of fill in the letters in the blank spots that you have, and then when you get back to the ones that you've got done, they should still be in order. Does that make sense? Okay, and I'll try to answer questions if we need to, but just to kind of check to see if you're getting the right order of things. So if we start with O, everybody find O on your page if you did it. All right, here's what the order should be. O, K, E, R, A, L, T, G, N, C, D as in dog, F, P, J, Q, B as in boy, S, I, M, H. Raise your hand if at least the ones you did you got in the correct order. All right, so you're going to get more practice with this in the actual practice for the homework. So this was just to kind of get you thinking and moving around and doing some stuff. But there's one more example of a problem that I want to go through before we're done here today. And that is to go backwards. Okay, so now I'm showing you what the graph of our function looks like. But what you don't see is what's the actual equation for it. Believe it or not, the process for doing this backwards is the same as the process for doing it the other way. If I give you the function and I ask you to graph it, we said that our process was to first identify the parent, then identify your AH and K values, and then graph, right? Going from equation to graph. In order to go from graph to equation, you're still going to start out by identifying what parent function was it, and then try to identify the AH and K values, but based on the graph now in comparison to what the parent would look like. And then from that, you should be able to write your equation. Okay, so in this case, what's our parent function? X squared. So we know we're dealing with the parent of f of x equals x squared. Okay? So let's figure out the a, h, and k's so we know where to plug those in. So does it look to you like there's an a value other than 1? So is there a negative a? No, because it opens up. And does it look narrower or wider than what a normal parent parabola would look like? No, because from our vertex, it's still 1 over 1 up, 2 over 4 up, just like it would be on a normal parabola. Okay? So we can assume that our a is just going to be a 1. Okay? How about h value? How are we going to figure out the h value for this? Okay, and which way would the h value be transformed? Left or right. So, from a vertex that's normally at 0, 0, how far did my parabola have to move left or right? 2 to the left. So that means h is going to have to be -2. How about my k value? That's up and down. So how far did it have to move from the original 0, 0 vertex? Down 3. Okay? So, g of x would look like what? Exactly. If you want to put the 1 out there in front, just for emphasis, you can. It's not necessary when it's just 1. But our h being -2 means we get x plus 2 in the parentheses being squared, and our k being -3 means we're going to subtract 3 there on the outside. Okay? So, most of your homework is going to be, here's your function, come up with a graph of it. But there's a few problems at the end that flip it around and say, here's the graph, now write the equation for it. Okay, so we need to be able to go both ways, and that's what you'll be practicing in the 1.2 practice, which is on Canvas, and that will be due for Friday. Okay? You can go ahead and get packed up and wait for the bell, please, before you leave.